All right, welcome everybody to the To My AI lecture series. Today we have a special guest. We have Ruchi Gao, who is a research scientist at Google DeepMind. She has earned her bachelor's degree of statistics from Peking University, and she obtained a PhD from UCLA. She is very well known in the research community, of course, because she's at the forefront of generative models, representation learning across all kinds of modalities. She has worked on a lot of multimodal work as well. Specifically, however, also on videos in 3D. And there have been a lot of cool works that she led, contributed, like ImageN, Cat 3D. And it's super exciting to see one of the great researchers from DeepMind here today. And her title is already about world models, which obviously everybody's excited right now. So we are super lucky to have you today, and we're really looking forward to your talk.
Yeah, thank you so much for the great introduction. And hi, everyone. I'm Richie. I'm super happy to be here to talk about some topics people are excited about recently. And please feel free to interrupt me in the middle. I would love to have some interactive discussion through the talk. Cool. So today we're gonna this is a very big title, by the way. So I will probably just cover certain aspects of these topics, but I may not be able to cover all different aspects of this topic. And also this is based on a lot of work from the amazing colleagues I have at Google DeepMind and collaborations with external students. So thanks for all my amazing collaborators for contributing to this exciting field. So I think we have seen a lot of success in digital assistant or development of digital artificial intelligence in the past decade. And then the next big questions people are constantly thinking about is when we can achieve the so-called embodied AGI. Based on my definition, what is an embodied AGI is, it's we want to build agents that are capable of understanding, reasoning, and interacting not only with the digital world, but with the real physical world. And we have already seen a lot of success in this field. For example, we see great improvement, progress in autonomous driving, and we see very exciting improvement in terms of humanoid robots. And eventually, what we want to have is the multi-agent interaction, so people can interact with robots and robots can collaborate with robots, and it opens a lot of very exciting applications in the future. So how to achieve that? So I think I want to mention those pioneer works in this field, starting from 2016, my co-workers at DeepMind who has this amazing work at AlphaGo, where they show if you really train an agent in this specific domain playing Go game, it can already outperform most of the human. And in 2020, we show some great work on train good agents solving 57 games. And AlphaStar is another example where we can train an agent to again outperform human as long as the environment is kind of clear and restricted. But in reality is, if we really want an agent that is generalizable to the real world, the world is really complicated, right? We are facing many new challenges every day. We are going to new environments, traveling to different places every day or every year. So such that those domain-specific agents unfortunately cannot generalize well enough so that we can easily put them into new environment and hope they can just catch up with all the different tasks we hope they can do, just as human can do. So if you think about the capability of an agent, it is really upper bounded by how complicated the environment is and how we train those agents in those complicated environments, and whether we can get enough signals from the environments in a safe way to train the agent. And I want to quote some statement from the two very famous scientists in biology, which is if you think about how organisms evolve, they are not passive recipients of environment pressures. They often modify their environment and thereby affecting their own evolution of and that of others as well. So that means like, our human or other like creatures, the evolution process is really like a active interaction with environment, and sometimes we even change the environment, and in return it affects other like creatures or humans as well. So how to train a general embodied agent? We really need like a world models that is able to simulate the diverse environments and interactions. And to define a world model, I think this is a very general definition, which is a probability distribution of the current state, given the historical state, and also the current action. So how to train a world model? I think, as I mentioned, like we already seen like very good capability of an agent if the environment is like perfectly in distribution of what we train the agent on. But if your model is not generalizable, or it cannot generalize out of distribution, what should we do? I think the very simple, the very first steps we should try to push to limit is like, well, we should just like collect the diverse data as much as we can, and we train the model until there's nothing left out of distribution. I'm not saying like this is the end of the world, but I think given the current era of like large scale model training, we should try to push the limit to this end until we reach the limit, and then we should think about like what we should do next. So how to train the world models at scale such that we can achieve the scenario where like we can cover most of the cases in real world, right? Then we need to think about what kind of data we have that is general enough and easy to get. So a very natural idea is like, okay, we have actually web scale video data that depict the real world kind of accurately because they are like ground truth observation, but they are not like perfect like full observation of what's going on in the 3D world, but it's like kind of like good partial observation. So in that case, which means like a very simple formulation we can get from this probability distribution is like we can assume ST, which is the current state, is a video frame or some representations of the video frame, plus maybe some other modalities that is helpful for us to understand what's going on with the current frame. And the action could be just like any intervention that happens to the current time frame of the video. Okay, so this is probably the formulation I'm gonna like trying to focus on for today's talk. And I'm just like wanna give a big picture of like what the a regular recipe for training the embodied agents at scale could be. So we can follow like very like classic training recipe that people have already verified in large language model regime. First, we can pre-train a model on all web scale video data. And at this step, we hope the model can learn basic physics information and how this physical world like develops given certain actions. And then the second stage, we do pulse training, generating challenging tasks using our model that involves, for example, long-term planning, long-term reasoning, or understanding complicated physics. And at this stage, we hope our model to have a more narrowed down scope, but it's more intellectually smart and more accurately depicting how our world evolves with certain like very more accurate physics. And then the third stage, we can rate or pick the interesting or high reward samples from our world models. And at this step, the generating of the samples might involve some like back and forth between the world models and the agents. And finally, we use the high reward samples to train our agent, to teach the agent, learn some like complicated physical tasks. So if we take a look at some statistics, about like the interest in terms of world models, here I just do a very like course summary of the percentage of papers on CS archive category that has world models as either the keyword in the title or in the abstract. We can see there's a very obvious like increasing interest in world models. And in particular, there's like a very big jump starting from 2022. You can see like the increase of the percentage has a very like big acceleration after that time. So if you take a look at what happens this year, right? I would say like starting from 2022 and also 2023 is really like we have seen a lot of big progress in terms of media generation. And it's the first time we see like, if we train those like generative models for image and videos at scale, you can see amazing like generalization capability where the model is capable of generating some samples that we know for sure do not exist in our training data set. And we see many big progress, many big projects from different companies and different startups and also academia. And it's another side note, a lot of like those projects are powered by diffusion models. And starting from 2023 until now, we see like many more, even more amazing like video models and image models coming from different places. And again, it's like repeatedly verifying, like if you train those video models at scale, you can see or unlock very physically realistic generations. So it's a very exciting area. So if we revisit this plot, we can see like, it's kind of like strongly correlated to the birth of like media generation, image models, and video models. So again, I feel like a natural idea is like, how do we, steer those amazing video models to serve as world models such that we can use them to push the boundary of physical intelligence, physical agents more. So this is like today's agenda. I will start from, revisiting like how video diffusion models develop over the past few years. And then I will talk about how we go beyond just purely video generation and how do we use video models as a potential strong candidates of world models. And finally, I want to discuss about remaining challenges of using video models as world models and discuss maybe some other alternatives. For example, we might be able to pipe in some 3D or 4D representations to solve some problems that video models currently face. Okay, so let's start from video diffusion models. I know like probably a lot of you have already been familiar with this topic. So I will start from like, why diffusion models, what makes diffusion model great as a candidate for media generation. I want to start from a very simple like viewer experiment. So I would name it as like there's some like blind spots of human perception. Namely, if I present you the following two images, could you tell the difference between the two images? Like, I feel like if you present those two images to me, I probably like if you just like give me like 2 seconds, I could not notice any difference. If I stare them for a bit long, I can notice that some like texture details are different on the table or on the bag. But if you take a look at the data, they're actually quite different. So on the left, it is a standard 8-bit RGB data format where I plot a histogram in green color. And on the right, it's like we reduce the data from 8-bit to 5-bit, which means like we reduce the number of possible values of that the image can choose from 2 to the 8 power to the 5 power. And as you can see from the histogram, the number of values that the data has are much sparser compared to the image on the left. But to our human perception, we can barely notice the difference. What if we keep doing this like compression repeatedly? For example, we can keep going on from 5-bit data to 3-bit data. And now we can see more clearly like the difference between them. And if we compress it from 3-bit of data to 1-bit data, we can clearly see the difference, right? So that means like, assume like our full observation or our full data distribution is 8-bit, but there's a difference in terms of, the importance of different bits of information of a viewer signal to our human perception. More precisely, human perception varies in sensitivity to different bits of a viewer signal. And on high level, perception is like much less sensitive to high frequency details and much more sensitive to low frequency content. So that means like if we purely build generative models based on likelihood estimation, we might like spend a lot of our model capacity to capture certain bits of information that are not important to human perception at all. So let's take a look at how diffusion model tackle this problem. So this is just like a very brief overview of what diffusion model is doing. So we have like two processes, one forward diffusion process that gradually degrade the information of a clean signal, such as an image, to pure white noise. And then we learn a reverse denoising process that gradually recovers the clean signal from white noise. And what interesting is, if we take a look at what's going on to an image with the forward diffusion process, it is like a linear interpolation between the clean signal and the white noise. And we can project this linear interpolation to the Fourier frequency domain. And it corresponds to the same linear transformation for the Fourier component of the signal. And we know, like for a natural image, the magnitude of the frequency component will decrease as the frequency increases. That means, like, on the other hand, if we take a look at the spectral power spectral of like white noise, which is depicted in the red color, it actually remains constant across all different frequency domains. So that means like if we only add a small amount of noise to the clean image or a clean video, only the low frequency components will be destroyed. And on the other hand, if we add like large noise, then the low frequency component of the image or other like visual signals will start to be degraded. So that means like if we follow the forward diffusion processes, then the first thing being destroyed are the high frequency details from the signal. And the only when we add a crazy amount of like noise, then the low frequency content starts to be degraded. This naturally gives us a very good inductive bias about how we destroy the data in diffusion process, which means if you think about the spectrum from clean image to white noise, then at the low noise level, the model is required to capture both the high frequency components and the low frequency components. But if we build a model that is on high noise levels, then we're kind of like trying to build a model that is specialized for capturing only the low frequency components of the signal, which according to our previous experiment, it is more important to human perception because it contains more high-level content, high-level semantically meaningful structure of the signal. Okay, and let's take a look at the training objective of diffusion model. I think one important factor of the training objective is it is not a purely likelihood-based training methods, which means like we're not training the model to directly optimize towards the likelihood of the data. This is true for other type of generative models. For example, for VAE, for energy-based models, for flow-based models, we just like purely optimizing towards the likelihood. But for diffusion model, because of this diffusion process, we can actually control or balance the importance of different frequency components by inserting a weighting function in front of the standard elbow or likelihood objective of our signal. And I think this weighting function is critical for the successfulness of diffusion models, because here I plotted a lot of like different like frameworks, diffusion model regime, where people use different weighting functions. But as we can see, there's a lot of like existing weighting functions people used that are monotonically decreasing as the log SNR increases, which means like all these like different frameworks that leads to one a consistent trend, which is like they want to downweight the regime where we try to model both the high frequency details and low frequency content. But we want to upweight the regime where we let the model to focus on low frequency component only. Which means like if we, with this reweighted objective, the model spends much more capacity on modeling like low frequency component, which is crucial to human perception. I mean, if we assume like our model infinitely capable. This is probably like doesn't matter. But in the current regime, our model capacity is still finite. Then this reweighting of different bits of information in the data is really important for the successfulness of a general model in zero domain. And another thing I think is also very important along the same line is whether we like the application or like the adopt for latent diffusion model. I think it also like has a similar flavor as the weighting function of diffusion model training objective, but it's used like a more explicit structure-wise like change to compress the data towards, again, like removing the really less important bits of information, but with an explicit autoencoder. And more explicitly, when we train this latent diffusion model, we usually introduce a very classic structure, which is like a VAE plus again. But I think people underestimate how important this scan loss is. Usually, the scan loss in the modern, like big like autoencoder or latent diffusion model training regime, they will rely on or define on some perceptual features of the patches, for example, dino features. And these dino features or some like other perceptual features give us a strong inductive bias, meaning that if the model already reconstructs the signal, that we cannot realize how different those features are perceptually, so we don't care about them anymore. And this also again give us inductive bias, being that in the latent space we only model the bits of information in the data that are semantically useful or important to human perception. And this allow us to reduce the dimension of the signal pretty aggressively. And this is also quite important for the video models to be able to train on the modern like architecture or hardware. And I think this open up some like interesting questions in the future, which is, are there any other ways that we can leverage this kind of perceptual inductive bias to make the training of diffusion models even more effective? I just highlight like a few works. I think that is really interesting along this line. For example, in this REPA work from Saining's group, they try to align the diffusion intermediate features with some pre-trained perceptual features, again from Dino network. And they show like if you align the features of the intermediate representations of your diffusion models, you get a huge boost in terms of training efficiency. And there's some other work, for example, this flex talks, where they try to build this inductive bias by this random dropout of discrete registered tokens in a nested order during training, which means like during training, we randomly drop out some tokens in the end of the sequence and let the model to only leverage the first few tokens to achieve these reconstruction tasks. This is another like very natural inductive bias we can pipe into our model architecture to make the model be aware of, we should have some semantically meaningful tokens and some like less semantically meaningful tokens in order. Of course, this is only like one aspect about why diffusion model can be successful, and there are many more things like diffusion models have done right. For example, they leverage this very simple regression-like objective, which make it very stable for scaling up compared to other type of diffusion models, other type of general models such as scan network. And it kind of like break this big generation problem from mapping to pure white noise to clean signal to a bunch of like smaller tasks in this divide and conquer like fashion. And also the way sharing across different like denoising steps kind of help the model to borrow strengths from each other's. It's also kind of like a data augmentation task that make the training algorithms more data efficient. Okay. And next, I'm gonna briefly review, how people leverage diffusion models in video generation regime. I want to start from this like kind of like old working 5 years ago, which is done by my colleagues at Google Brain, where we literally just start from exploring how we can leverage the best architecture people use for image diffusion model at that time for video generation. And back then, people are still using this UNet architecture for image diffusion models. And the simplest like generalization we can think of is to generalize the UNet from 2D to 3D by adding a temporal attention layer across different frames to explain the correspondence across different frames. And then we keep all the other components the same as the 2D UNet used for image generation. And at that time, we showed some very interesting results on 64 by 64 image video generation. Actually, it's already like a text-to-video generation task, but it's a condition on very simple text description, for example, a single word firework. And we can generate reasonably well videos on low resolution. And after this like first pioneer work, we try to generalize or scale it up to some high resolution video generation. And back then, there's a popular network which is called Cascaded Framework, where the idea is like we assume like we need to spend a huge amount of capacity to capture the signals at a relatively low resolution and low FPS. And then starting from the low resolution, which is a base model, we train a sequence of super resolution model both temporally and spatially, and finally get the high resolution videos at 720p 24 fps. And for doing that, at that time, the best setting we empirically get is to make this super resolution as detailed as possible, which means like each step we only do a small step of super resolution, either temporally and or spatially. And the whole pipeline end up with being like 7 models. But this has a lot of like problems. For example, there are too many models to train and tune, and we quickly see some error accumulation by piping all these like different models together, and makes like serving models to be quite expensive. If we want to serve these models to like a lot of users, we need to have 7 models in the serving hardware at the same time. And I think another critical problem of this type of cascaded framework is it's really hard to do any type of scaling study, which means like if we want to predict how the model behaves from a small scale model to a large scale model, which is quite important to the current like regime of large scale model training, it's really hard because it's hard to predict, how whether if you change one of the model in the pipeline, how it will affect the whole performance in the end. And then later on, we see like Sora came out. It is a very pioneer and like milestone work, which again proves this bitter and sweet lesson, which is less and more. They only have one single latent diffusion model in the whole pipeline, and they apply this diffusion transformer architecture, which is literally like we encode the video as a 3D cube of latents, and then we flatten the 3D cube of latents to a 1D latents, treat them as the same as large language model tokens, and send them into a big transformer. And what's nice about this framework is it's very simple. It's only like a single, it's still like a 2-stage training procedure, but we only have one big transformer model to worry about. And a nice thing about diffusion transformer architecture is in the original DID paper, they showed like diffusion transformer scales pretty well with both increased compute and increased model size. And another feature that this architecture natively support is arbitrary aspect ratio generation, because for different type of like aspect ratio, if we flatten into 1D sequence, then they don't have any difference. We could just like pack them into a single sequence and treat them as like a 1D sequence signal to the model. And after that, at Google, we also start to explore something similar. So we abandoned the cascaded generation framework and switched to this latent diffusion model framework. And we released our first version of the model in May 2024, where we name it as Will, and we can generalize reasonably high quality, high resolution videos with this framework. But I see a lot of problem of view one. First of all, the motion is turned out to be slow and not diverse enough, and the model sometimes can produce unrealistic physics, and some hallucination happens from time to time. And also not great on text following. If you ask the model to do some complicated actions, sometimes they just ignore what you describe in text. So if you ask me if video models are ready to serve as like a realistic world model to simulate accurate physics at that time, my answer is probably no. We need like more effort on pushing the limit of video generation model first. So we just like keep pushing, and then in December of 2024, we released a second version of Veo, where we are able to create videos at an even higher resolution, up to 4K, and the model is able to understand camera controls in prompts, for example, wide shot, POV, and drone shot. And more importantly, we try to let the model to better recreate the real-world physics and also realistic human expression. And then 5 months later, we released the third version, which is Veo 3. And at this version, I think the most important feature is like we integrate audio. It's a native model, multimodal model that generates video and audio all in once. I'm not sure if you can hear my audio, but I will try.
This ocean, it's a force, a wild, untamed might. And she commands your awe with every breaking light.
And it can like synthesize or generate like sounds of different aspects. For example, it can generate sound effects, ambient noise, and also dialogue.
These young people nowadays, with their new technology and new ideas, it's all rubbish.
I think the capability of being able to generate dialogue is also a very important step towards like training good agents, because a lot of like capability of agents can be achieved through like communication across different agents and like through dialogue. And also is doing better in physics and realism. And another important thing is like we try to improve prompt adherence following a series of actions and scenes with greater accuracy. And more importantly, the model is capable of following text instruction in time order. Here's an example. If we give the text prompt being that a dedicated feature rests on a fence post, a gust of wind lifts it, sending it dancing over rooftops. It floats and spins, finally caught in a spider web on a high balcony. As you can see, this description is not only describing what's going on in the world, it also has a very strong time order of what events happens first and what events happens next. And let's see what the model generates. It's able to generate like, or synthesize how the actions or the events develop over time accurately. Okay, so after we see those like good video models, next question is like how do we steer those models to be good world models? And I think the very first thing remind me like is like how do we control the video models with the actions? Here I want to talk about like an effort from GDM, like Google DeepMind, along this axis, which is a Genie series of models. This series of models start from a first version where we try to frame the action to be some later representations, where we hope the model can learn those later representations of actions purely unsupervisedly. Here, this is the Genie 1 architecture. We're given a sequence of frames. We have two branches of model. The first branch is to try to tokenize or understanding the videos, and the second branch is try to learn a sequence of later representations of the actions. And then in the end, there's a dynamic model try to merge those two representations together and try to predict what's going on for the next frame. And this line of research allow us to learn some good later representations of simple actions in the format of keyboard mouse. But the problem is like with those latent actions, it's kind of harder to generalize to more complicated actions. For example, the car moving, or like some jumping, such like this type of things. So in Genie 2, we switch to a different approach where we let the model to be explicitly conditioned on those keyboard mouse actions. And here we can see like those videos are generated by some user input keyboard mouse actions explicitly. And behind the model, the architecture is very straightforward. We use like autoregressive video diffusion models, which means we generate one frame at each time. And when we generate the frame, it's conditioned on all past frames. And it is a latent diffusion model similar to Sora and similar to Veil. And the advantage of like autoregressive video diffusion model is we can get response from the world model faster because we don't need to wait until the model generates the full sequence of videos. We can basically get it in a streaming fashion. It is more like suitable for the cases if we want to train the agents in a closed loop learning or online RL fashion. It also put additional challenges to the modeling side because this autoregressive architecture assumes there's a causal attention mask for the layers to capture the correspondence. It constrains the model capacity compared to the case we assume there are fully bidirectional attention mechanism across different frames. What I think is very interesting is like in Genie 2, we show this like a prototype about how the world model can interact with an agent. Namely, we have this SEMA agent model, which takes text and the current observation and try to predict what the next action should be in keyboard mouse format. And then we can, given the current observation, predict the agent action from this agent and feed the action to the Genie 2 world models and predict what's going on for the next frame. And then we again feed this next frame prediction back to this agent, predicting the action, and so on and so forth. So it closes the loop of how we can achieve a task in the simulated world. And here's an example. If we are giving the same like initial frame, but on the left we give a text instruction being that open the blue door, and let's see what's going on. The model will be able to predict the actions to go to the blue door, and the Genie 2 will be able to predict what's going on with the sequence of actions. And on the right, if we give the instruction to be open the red door instead, the model will be able to predict a different sequence of actions, and the world model will be able to predict what's going on with the different sequence of actions. And this year we released Genie 3, which is again an upgrade of what we can achieve with this like Genie 2 model. And we mainly achieve across the following axes. We improve the model quality. We improve the horizon of the videos that the model can generate. So here's the comparison between what the Genie 2 video look like and how we can achieve in Genie 3 with the same text prompt input. Okay. And if we compare the different capabilities, different model unlock, starting from game engine, which is a previous work before Genie 2 on this explicit action condition regime, and to Genie 2 and to Veil and to Genie 3. The nice feature of Genie 3 is really about like the real-time fashion, and it can generate the video as long as to like multiple up to like multiple minutes, and it also supports like action control pretty accurately. And of course, keyboard mouse action is only the first step or a prototype of that. In real world, we might want some other more accurate or physically plausible control. For example, we might want some like motion control where we define the exact movement of objects by selecting an object and define their moving trajectory. Here is an example where we show we can steer the view model to do this type of action control, but by providing the bounding box of the object and a moving trajectory. And on the right side, we show like how the generative video can follow the movement of the objects we gave the model as input accurately. And another quite important control is camera control, because think about like the agent is like trying to navigate in a new environment, and they wanna move around and look at different angles of the room. A very natural thing to do, or a very natural representation about this type of exploration, is in the form of camera control, where we can define the location and the viewing direction of the agent. And another, I think, very important thing is like the scene plus character control. For example, if you wanna put the agent into different worlds, different environments, and let it to behave like consistently, then we might want to be able to combine the character or reference with different worlds. And here I show an example where given like an image of the character and an image of the world, how we can steer the view model to generate a video that is consistent with both the character and the world. And of course, this is just like a very initial step where we only have very partial observation of both of the character and the environment. But I think in the future, we need like even more accurate or more detailed control about both of the two components. Okay, and next thing I want to briefly mention is like multimodal models and why that important to world models. So why is multimodal important? Because very simple, because our model or our world is generically multimodal, and we are using like most of the time we are using like signals from the world beyond only visual signals to guide our actions or our plans. For example, if you're navigating with an environment, and you hear something or smell something from an angle, even if you did not see anything, you know that there might be an enemy that threatens you, and you know what the action you might want to do. And another example is like if we're in a math class, and we're not only seeing like those blackboard visual signal, we are trying to extract the text information from the blackboard and try to do some derivation from the text domain. And another example, if you want to train an agent, a robot to lift something, if you don't know the metadata of the object you are trying to lift, for example, the weight and the textures, it's very hard to predict how much strength you want to use to lift this object. So there are a lot of like more signals we want to leverage beyond just only like what we can see from the world to be able to achieve some complicated tasks. And another very important thing, I think, is like if we train the model in the multimodal regime, we might be able to unify the world model and the agent in a single model, which namely like we can let the model to output both actions and the observations given the actions. It also supports better in terms of your thinking and reasoning, because if we can wrap both like the world model and the agent in a single model, then we will be able to propagate the reward signal into this single model and update or improve both of our world model and the policy within the single like reasoning or thinking fine-tuning. And another more longer term goal I'm very excited about is like if we unify those two tasks in a single model, maybe we can get a better inductive bias to compress the visual signal more aggressively compared to the previous like inductive bias I talked about, where we just like try to see what's important to human perception. Maybe we can try to see what is important to achieve certain tasks. And then we can compress the visual signal more aggressively by removing the signals that is important, might be important to human perception, but not important to achieve certain tasks. And over the past 1 or 2 years, we have seen increasing interest in terms of interleaved text plus image generation. That I think is a very important step towards this goal. The formulation is very simple. We just interleave the text and image generation in a single sequence, and we let the model to autoregressively generate either a text token or an image for the next placeholder in the sequence. And if we consider text as the action, the image as the state, then this type of interleaved text plus image generation as try to model the following 3 probabilistic distribution in the same time. And it precisely corresponds to word models, agent, and agent with a mental world model at the same time. So I think, and another question people trying to solve or trying to still debate is for multimodal generation and for the media part, do we use continuous or discrete tokens? Do we use autoregressive formulation or diffusion model? And we see different trials in different regime. For example, this Chamalong from Meta, they assume all different signals are organized in discrete autoregressive fashion. And we see this Show and some other follow-up works where they try to use discrete diffusion for image generation. And we see many more other works, for example, Transfusion, Bagel, they use this type of hybrid approach where we use autoregressive generation for text domain and use continuous diffusion for media domain. And I think there's a pros and cons in terms of which model formulation we use. If we use discrete autoregressive formulation for media generation, the very biggest advantage is we have this unified training objective, unified formulation for vision and text domains. We might be able to see positive transfers across different domains more easily. And it also has a very simple hyperparameter design space. There's no weighting functions, no schedules, sampler we need to worry about for discrete autoregressive generation. But meanwhile, I think there's a very big challenge there, which is the sampling procedure is not flexible enough. It's kind of slow if we restrict ourselves to be in the regime of next token prediction for video generation, because it will be too slow for real-time applications. On the other side, continuous diffusion has this big advantage of we can leverage a lot of flexibility or improvement in sampling. We can do distillation, we can do guidance, we can do advanced ODE, SDE samplers to improve the sampling speed and improve the controllability of the action or text following. But again, I think there's also a big challenge for using continuous diffusion, which is because of the training objective is quite different from text. We are leveraging an elbow, not a likelihood-based approach. We are adding noise to the training data. It's quite different from the clean tokens we see from text. It's very challenging to balance or to let the 2 regimes to have positive transfer between each other. So I think there's still a lot of open questions we can tackle along this regime. First of all, for word models, what is the unified definition and the formulation of actions we should leverage? Should we define all different actions in text, or a structured JSON file define different actions? Or do we have to rely on some multimodal format of actions? For example, the motion control I talked about. Maybe we want some more fine-grained control in format of multimodal. And can we find, a unified representation of image and videos that handles both understanding and generation tasks? Should that be a discrete representation or continuous representation? And what is the best representation we can achieve that enable positive transfer across different modalities to the maximum amount, and meanwhile also satisfy the serving constraint, satisfy the sampling speed constraint we might face in real world applications. And for image and video, do we use autoregressive or diffusion or something else? And in the most recent few works, we see like maybe pixel space diffusion can have more like potential than we actually thought initially. Should we switch back to pixel diffusion? Should we at least revisit pixel diffusion at scale? These are all interesting questions to tackle. Okay, finally, I want to talk about remaining challenges of video models and talk about how 3D and 4D representations can still have like great potential in those regimes. Okay, I think the very big challenge is, how do we maintain long-term consistency? For long-term consistency, it's very important because if you want to train an agent that navigates within the world, we cannot only expect it to navigate for like a few minutes that Genie 3 can now achieve. We might want them to, navigate for like hours and to achieve. And I think like for long-term consistency, it contains two parts. One is, the static part of the environment should always remain static if there's no change in the static parts. For example, if a person went outside of their bedroom and came back later, a few hours later, then the room should still remain the same room. It cannot change to a completely different room. And another more challenging part, I think, is the dynamic parts of the scene. It should progress over the time reasonably well, even if it is outside of the current field of view of the agent. For example, if a person pan-fried an egg, and then it left the egg being pan-fried and did something else and came back later, then the egg should be cooked with time passing by reasonably well. It should not remain as a raw egg. So how do we teach a model to understand the concept of time, even if it is not within the current field of view of the model? It's another very challenging task. And how about we just put the bet on, we further make the context longer and we further scale up of our model. Can we just solve this task eventually? This is a very hot bet that a lot of people put on. I think there are a few challenges of this bet. First of all, it's not efficient. We will probably hit the context limit with videos much sooner than what we hit in language domain. It's very, very unlikely to fit like an hour video into the context with this naive long context approach with the current hardware. And another even more critical problem is it's very hard to find such video data at scale. For example, if you wanna mine 1 hour long-term exploration video from YouTube, it's very rare. Even if we can find them, it's not diverse enough. And unlike large language model domain, we can easily do synthetic data. It's again very challenging to synthesize realistic video data to be able to train high quality model on those data. So I think for long context problem, data is another limit we will hit maybe sooner than the hardware limit. So how could we make the model to be able to train on a more generalizable fashion or more data efficient fashion is a critical problem. So what is the potential alternative, right? So let's think about what's behind the video. It's actually an entire 3D world. I quote something that Alyosha mentioned quite often, which is if you think about the pixels in 3D world, actually more than 90% of the pixels are static. But we still see a lot of dynamics in videos. That is because a large portion of the pixel changes can be explained away by purely camera movement. So can we disentangle camera motion and the scene dynamics in a reasonable fashion? And more importantly, can we maintain a memory that does not grow linearly as the number of video frames, but only grow when the actual 3D world expands or there's actually new events happening in this 3D world? That's an important question. And potential solutions, how do we avoid memory growth linearly over time of videos? I'm just posing a few I think promising approach. One is we can borrow some inspiration from the language model regime. We can do some retrieval-based methods. So here's a demo from World Labs where they try to do camera-based retrieval, where when you generate the next frame, you don't condition on the full long context. You only select the most relevant history spatially. In the future, we might be able to combine this with a few frames temporally happening that is closest, like in the most recent history, basically, and maybe combine that with, the most relevant history, spatially. And we might be able to train a stateful model. This is for example, we may not be able to, maintain a very explicit state, but we can maintain an implicit state that progresses over time, but the size of the state does not grow as the time increases. For example, we see some work recently that using state space model or test time training architecture to maintain such kind of state. And we might be able to explore some more explicit, like 3D representation of the world. For example, this is a work from Gordon's group, where they try to condition on a 3D point cloud for the static part of the world, and then we generate the dynamic part of the world online. And the next challenge is, the real-time interaction perspective. We see like, the Genie 3 can achieve real-time generation already, but if we want the model or the agent navigate and interact in the real-time fashion cheaply, it's still very challenging. For many use cases, this actually is crucial. For example, if we want to train the agent by using this cheaper hardware, for example, AR and VR glasses, it's impossible to deploy like a big video models to those devices and get the feedback in real time. So how do we solve this, serving costs of the current video models in real time? This is another critical problem. And we know, on the other hand, we have like amazing 3D representations that can perfectly achieve this goal, that we can serve these 3D models in like cheap devices in real time, infinitely, as long as what we want. So, and if we get enough captures of the 4D world, we can even generalize this type of 3D representations to 4D representations and replay the dynamic scenes as many times as we want. So the question is how do we combine those two things together, right? On one end, we have some 4D representations that allow us to explore the 4D things as many times as we want, but and we only need to pay one-time optimization costs, and then it's basically free to explore. But the downside is it's exploration only. We cannot interact with them. We cannot create new events or control them easily. On the other hand, if we have a good, fast video models, we can interact it with very diverse actions, but it's very expensive to serve per action model code. So I think we need to find a good way to combine the best of the two worlds. And we have this line of work where we have a very first step, a very prototype to try to combine these two worlds, which is Cat 3D and Cat 4D. The regime is, the approach is very simple. We just treat the fast video models as a way to generate the observations of the 3D or 4D world. And then we do 3D or 4D reconstruction, treating those generative frames as observation of the world. And we have a follow-up work where we try to merge those two steps together, where, for example, if we are given like a multi-view video model or multi-view image generation model, we fine-tune it to generate the 3D representation directly, such that we don't have to have this generation and then reconstruction two-step approach. Instead, we can generate them all at once. That makes the whole system even faster and more efficient. And this is led by an intern at our team. And I think Stan is also on the job market if you guys are trying to hire them. Okay, so here's the closing thoughts. For the video generation, it has been developing rapidly over the past few years. We have seen initial promising usage in real-world content creation for leveraging the current video models. And if you steer the video model to be more controllable, we might be able to use it as a very promising candidate for world models. And if we can further extend it to be, an interleaved generation for both actions and the worlds, it might be a nice way to combine both the world models and the agents into a single model. But we might need more thoughts on what the unified representations of the media domain should be, and also the action domain should be. And there are more challenges we need to tackle. Namely, I think the long-term consistency and the real-time chip interactions are the two big problems we need to think about more. And there might be some more efficient representations, either implicitly or explicitly as a 3D or 4D representations we might be able to leverage to solve the above two challenges and get a good synergy between them and video models. Yeah, I think this concludes my talk. Thank you very much.
Thanks so much. Really awesome. Really cool. So yeah, we have time for questions. So we can, we also have a few on YouTube already. I'm not sure if I can go through all of them. But obviously here people can ask questions. I'm going to start with a simple one. And then if you want to ask a question, unmute yourself and also show your video. I'm going to start a question on the multimodality because I think this always fascinated me. So obviously for like image generation and image diffusion models, right, the text conditioning was kind of instrumental to get enough training signal to make the whole thing work. So I'm really curious what your thoughts are for having it as an input condition versus generating as an output, because Veo 3 in a sense does the opposite, right? There's like, you generate the audio at the same time. Does it help there too? Is it making it better? Is it complementary?
Yeah, that's a very good question. I think like when adding the audio, we definitely observe like a quality boost, like across different metrics. So I think like it's easier to prove like there's some like positive transfer across different like media modalities. For example, the transfer across like a video and audio. Again, I think it's because like they are more aligned with each other time-wise. But I think it's more challenging if we want to see party transfer across like more different modalities such as text and video, because text is like a more high-level summarization of the media domain, and they're now perfectly time aligned for most of the time. And as I mentioned, like the training objective is different across those two modalities. So I think there might be more challenges if we really want to, unify the representations from, text to video and video to text. And this is something I think is a very cool, like, regime to work on.
Thanks. Any other questions?
Yeah, hi. I would have one question about multi-view diffusion versus video diffusion. I think one advantage of multi-view must be that you can explore scenes faster. Like if you want to look around an object, you can basically have 180-degree viewpoint change of a camera more or less directly, whereas in a video diffusion, you always have to generate the entire sequence up to that point. So maybe specifically for 3D scene generation, what's your take on multi-view versus video diffusion as a prior model to use for this task?
Yeah, that's a very good question. I think multi-view is, like you mentioned, it's like more steerable in terms of changing the viewpoint more quickly. But for video, because I think the data we train out for video is like more like a continuous like camera change. I don't think like we want to pick one of them, right? I think eventually it's more or less like a data question. Like if we feed the model like multi-view data more, it might be able to learn the multi-view like perspective more accurately. If we always feed them into those videos with continuous motion, it naturally learns to generate continuous motion for most of the time. I think we might be able to find I like a unified model that can do both of the two tasks. I don't think like there's like a fundamental limitation for like to avoid doing that.
Okay, cool. Thanks.
Cool. Other questions? There's a few more questions from YouTube. I'm just going to ask a few of them. Can you talk a little bit more about the temporal consistency, for instance, in the interactive video models, like when you basically have conditioning some very diverse actions?
I see. Yeah. So I think the long-term consistency is a very important question. And right now, I don't think there's a deterministic answer about how we can tackle them. Like I think if we have some 3D representations, then we can have perfect consistency because that's just like our representation is about, right? But how do we tackle the dynamic part of consistency, like I mentioned? Like if you don't see the event happening, but the time passed by, then you still need to have this type of like dynamic consistency. And that requires of more challenge about our model capability to be able to store the event somewhere and let it to progress over time, and then maybe we can revisit later this type of question. I don't have a clear answer about that part yet.
Hey, thanks for the talk. I've also a question. Since you were mentioning world models, you also need to have better understanding of attributes that might not be totally visual, like physical attributes, the amount of force, and all this kind of stuff. How are we going to get the information if the different modalities are largely going to be visual? Or are you imagining this being output in like a different kind of like text-based form or something?
Yeah, I think that's a very good question. I think like for some of the modality, maybe it's easier to get some data. For example, if you want to have like camera annotation, we have very cool, amazing like vision-based tools to estimate the cameras and maybe depth, for example, right? But I think there indeed some like certain modalities it's very hard to get, right? For example, for the grasping force, or like the detailed metadata of the object. So I think eventually, if you really want to achieve complicated tasks, some type of online RL type of algorithm is necessary, which means like we might not be able to learn all the full context of it at the very beginning, but we can try it for a few times and gather the information like in an online fashion. I think eventually it's a avoidable step to me.
I see. I mean, that kind of makes sense. I'm curious though, if you rely very heavily on visual data, do you think there's enough to get still sufficient information? Or are you thinking of the RL as based off of like physical simulations and stuff where it would actually provide harder constraints on whether things are actually physically correct?
Yeah, I think like for navigation type of tasks, right? If you just like explore this environment, you want to go to like a destination, this type of tasks, I think vision is really, really helpful. But I think for interaction type of tasks, right? If you want to like cut an apple, like, lift like an object, this type of more like interaction heavy tasks, I think a visual signal might not be enough. That's my current thought.
Do you have any thoughts on where the other signal might come from in terms of like synthetically generated or annotated or where we can get this?
Yeah, I think like synthetic generation, for example, if you have Unreal Engine, right, and you can render them, and also like doing annotation with, as long as we have some data, we can train an annotation model to, generate more like data, this type of like flywheel type of approach, where you start from a small amount of data and then you train a model and then annotate more data and feed it back with the higher quality subset of data. That's also a way to create the data. But yeah, I think in general, it really depends on case by case what kind of signal you want to do, right, and how difficult you can get those type of signals.
Cool, thanks.
I have another question about the whole argument. Are video generators world models, which I think is fascinating. I guess one question is always like, you need to have at least something like view consistency when you move the camera around. So, and there's a debate of people saying, well, if you can't generate the view consistency video models, kind of fix it locally. But there's the counter argument of saying like, okay, if you cannot distill it in a 3D representation somehow, then it's not a model, right? It's not a world model because it has an inconsistent physics underneath, or like even 4D, right? If you think about all the dynamics. So do you think it's just, I don't know, do we care about this distillation in a 3D/4D representation, or is it just something we kind of give up eventually and just, everything is just a video generated transformer?
No, I think like the 3D consistency is really important, right? For example, if we train like robots in this generative 3D world, it has to be like 3D consistent, right? Like it can be like, have some inaccurate depth. Otherwise, the robot might hit the wall like earlier than we actually imagined, right? So I think it's really important 3D consistency, and I agree with you. Like we don't really put enough emphasis on this problem at the current regime of video generation. So sometimes we see like the video are really realistic, but if we try to distill into the 3D representation, we will see a lot of artifacts, which means they are not 3D consistent enough or as good as we thought. So I think it's really important to build certain kind of evaluations that emphasize more on 3D consistent. For example, like distilling into a 3D representation and measure whether it's successful or not, maybe it's a good evaluation matrix, right? Or we might want to build on top of some like 3D view alignment type of matrix to measure like how 3D consistent our videos are. I think people start to realize that, but we still need more time to improve along that axis. And also, I think it's because sometimes our training data we don't care about 3D consistent well enough, right? If we have like some gaming data or like some synthetic videos in our training data, then the model might learn some noisy signals in terms of what 3D consistent means in real world. So if we really care about that, maybe we need some post-training stage to teach the model. You really need to care about 3D consistent by feeding them into some like high quality 3D consistent videos.
Yeah. I actually have one more question on the, what do you think about the scalability where we go with like current hardware? So for instance, if you're thinking about when the image diffusion models came out, I don't know, everybody thought, oh, wow, this is really crazy to train. Like we will never be able to do videos, right? And then what happened is like everybody jumped on the video models and it turns out, well, okay, you just need more hardware. So do you think it's just a scalability issue? You just add more quote unquote compute in order to solve long context issues and consistency and so on? Or do you think there's some other things missing?
Yeah. I think like we should leverage like different techniques at all different like levels to solve this problem, right? For example, if hardware improves, then we will be able to feed longer video. And then if like some attention mechanism like transformer architecture improves, maybe we will be able to get even longer video. And if we have some like better 3D representation, better spatial identity bias for video models, we might be able to improve it more. I don't think like it's like we need to pick certain level of technique to solve this problem eventually. I think it's like the future is really hard to predict. Who knows like what the hardware will look like in like 2 years, right? I gave up on doing prediction like that, but at least like for now, given the current hardware, I think it's still very challenging to fit the model in like to generate an hour video, for example, is at a high resolution. It's still very challenging.
Well, you just need more model charting across more nodes, right? I mean,
yeah, sure, yeah.
Cool, awesome. Yeah, I don't know. Is there any other last question? Because I think we're running a little bit over time. So at this point, I would again, thanks for the amazing talk. I'm gonna end the YouTube stream for now. You can still stay quickly in the call flow. So yeah, thanks everybody on YouTube also for tuning in. I hope it was great. Obviously, Richie's available. You can reach out to her, and you should check out her amazing papers. I mean, it's really cool to always read this. And she also had a really amazing blog post of diffusion and flow matching. I think a lot of people know that. I think it's really awesome to follow her work. Thanks everybody there. See you next time.
Thank you so much.
Okay, very cool. Okay, so I ended the YouTube stream.